So let's plot again x prime versus x. This is x prime and this is x. So the differential equation was ax times 1 minus x, and this was a parabola with x-intercepts at 0 and at 1. At 0 and at 1. So when x is less than 0, x prime is negative, therefore the trajectories are, the motion is directed towards left. And then we have, when x is greater than 0 and less than 1, x prime is positive and motion is directed towards right. And then we have, when x is greater than 1, x prime is negative, so the motion of particle should be directed towards left. So we can see that nearby solutions are tending away from 0. So tending away from 0, therefore 0 looks like its source. And since the motion is towards the 1, or the nearby solutions are attracted towards 1, so this is going to be sink. So how will our phase line look like? Let's plot the phase line. So the phase line will be, so let me keep the equilibrium solutions, which is 1 and 0. So this is x equal to 0. So we want to plot the solution trajectories, and we want to analyze the behavior of solutions. So this is my x and this is time axis. So let's see what is going on. So we have already seen that 1 was sink and 0 was source. Therefore we can have stationary solution over here at x equal to 1 and a stationary solution at x equal to 0. What is happening to the other trajectories which are starting, let's say, somewhere at x of 0 equal to some other value, let's say 0.5, x of 0 equal to 0.25, or etc. Then between 0 and 1, we have already seen that x prime is positive. In other words, the slope is positive. So slope field should be positive. And as we are moving towards 1, it is getting more like this. In other words, any trajectory that is starting from here will move towards 1, because 1 was sink. So nearby solutions will be tending towards 1. So in other words, the solutions are moving towards 1. Any other trajectory, let's say x less than 0, in this context, since we are talking about population, so population is not negative, but again the trajectories will move away from this 0. And in this case, if a trajectory is coming somewhere from here, then it will move towards 1, because 1 was sink. I hope that makes sense. So from here what we see, that as time goes to infinity, any trajectory that is starting here or starting at some initial data, let's say x of 0 is equal to 0.5 or 0.25, will move towards 1. Why 1? We can recall that 1 was our carrying capacity. So the population can grow, but up to certain limit, and that certain limit in this case is 1. But if we replace this n 1 by n in general, so what will happen? We can see that then this 1 will be replaced by n, nothing else will happen, so it will be 0 to n. So everything else will be same, the behavior will remain same. So let's draw some conclusion, but before we draw conclusion, we can also compare that we have seen that x of t, the solution was equal to x naught e power at divided by 1 minus x naught plus x naught e power at. So we can take some initial data, let's say 0.25, and plot this in Desmos and see that what is happening to the trajectory. Don't forget that we are plotting it into Desmos, so in this case the time axis will be x-axis and in place of x we have y. So let's plot the equilibrium solution, that is y equal to 0, y equal to 1, and then the solution that we have y equal to some initial condition times e power. In place of a we can keep a to be 1 for now, but this t was x, we have already seen that. Then we have I is initial condition 1 minus I plus I times e power x. So we can keep now I to be something, let's say 0.25. So we can see that the solution is every solution that is starting, that is every trajectory that is moving from here, and then the solution is moving towards 1. So we can change this initial data, let's say 0.5, 0.75, 0.8, 0.9, or maybe 0.01 or 0.001. So you can see that if the population fraction is very small, then it takes a lot of time to 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 reach to equilibrium solution or to the carrying capacity. But if the population fraction is very large, let's say 0.9, then it takes no time to reach carrying capacity, and that is 1. So we can see that. But what if we take I to be negative, let's say minus 0.25? This is out of context because population can't be negative, but again it is showing that 0 is source. So the solutions are moving away from 0. I hope that makes a bit sense. So the conclusion is, for x prime equal to ax into 1 minus x over, maybe you can keep n, the x equal to 0 is a source, or the trajectories are moving away from it. So x equal to 0 is a source. This is equilibrium solution, which is source, and x star equal to 1. In this case n is a sink. So in logistic population growth, the population in long run tend to n, or the carrying capacity. Thank you so much.